Okay, so two procedural things before we go into this last lecture. One is that tomorrow, late morning, we are going to post the third interim exam, which is going to be in the format of the first one. That is take home. You will have a little more than 24 hours to do it. And this time, you'll see right at the front that explaining any numerical answers that you get is as important as anything else. And then there will be the optional final exam a week from tomorrow. I'll plan to post review problems. It's going to be more similar to the second exam in terms of fairly short problems, and it will be in class, comprehensive. So this is about exams. The second thing is that I want to urge you not to forget the course evaluations. This is always important as feedback to the lecturers. And this year, it's even more important because this is the first time that the course is taught. And on top of that, you were exposed to some very different philosophies of teaching this course. For me, it was very good. That is, had I started to teach this course completely on my own, I probably would have included only a third of the Bayesian material that you had. Now my plan is, if I teach it again next year, I'll probably have 2/3 of it. So I need feedback of whether I should go even further or less in terms of your interest. And of course, there is the issue of the balance between teaching you to do things with MATLAB versus some of the issues of the big picture that I like to emphasize. So it's very important. Do us a favor and fill the course evaluations. What I was originally planning to cover today is actually to go over 3 slides, to go over several slides that you submitted. But looking at the submissions of the homework problem, I realized that different people had different levels of understanding of the different parts, and also there are some very interesting. So I asked Chen Yang to prepare a slide version of the solution that will be posted, and I edited it, and that's what we'll do most of the time today. I want to go over the solution as it relates to one data set. It's data set 3, and cover the points that are, I found at least, number 1, interesting, and number 2, possibly subject to misunderstandings. So this is the paper helicopter project. And I'll basically go over the 6 problems that were given there. The first one was to find a conservative estimate of the fall time from your measurements. And this is a matter of estimating the 5th percentile. This is typically done when you have a population. And so you end up with having mean and standard deviation of your fall time, and they are uncertain because of the fact that you have only 10 samples. And so you can produce a sample of means and a sample of standard deviation, and you can calculate from them the 5th percentile using the inverse CDF, or you can do it with sampling. And then for good measures, you can give either the mean and standard deviation of the 5th percentile, or as is often done, you add another layer of conservativeness and give the 5th percentile of the 5th percentile. This is in structural design. This is typically done. A basis, for example, is the 1 percentile of the strength distribution and then you take the 5th percentile of that. That is, so this is the way the FAA makes sure that the airplanes that you fly are safe. So the first helicopter of dataset 3 has this type of distribution, and it's important to see whether the results make sense. So for that helicopter, the mean was 3.78 seconds, the mean of the fall time, and the standard deviation was 0.37. And the mean of the 5th percentile that you see in this distribution was 3.18. And so we ask ourselves, is that reasonable? Could anybody tell me how would we check whether this is reasonable? This was done by sampling, but if somebody asks you what's the 5th percentile of this helicopter that has a mean of 3.78 and a standard deviation of 0.37, yeah, that is 5th percentile is about 1.6 or 1.64 standard deviation below the mean. And so if you multiply this 0.37 by 1.64 and subtract it from 3.78, you do indeed get 3.18. That is, so that checks. And then if instead of taking the mean of that, you take the 5th percentile, you go down to 2.88. So from 3.78 of the mean, a very conservative estimate is 2.88, which is about a quarter less. And this is the typical kind of material properties, a knockdown factor that we see the FAA requiring people who design airplanes to use. Yes?
How do you establish the distribution to sample from for the percentile?
In this case, it wasn't established. There were 100,000 samples taken, and so where the 5,000 is, this is the 5th percentile.
So like you found the normal distribution of the fall times and then sampled 100,000 from that normal
Right. Yeah, that is the assumption is that the fall time itself is normally distributed, and so yeah, right. Other questions? Okay, so this is problem 1. Any other questions about that first problem? Okay, so in problem 2, you wanted to compare the CFD of the prior to the CFD of the measure. It's sort of finding how different they are. The 0.5 to 1.5 CD distribution that I gave you was something based on what I read and what my experience, that when you measure the fall time of these helicopters, you typically get results of order 1. And based on what I've seen, I figured out that 0.5 to 1.5 is going to include any case that you may be able to generate. So that's the basis of that. Now, in order to take a distribution of CD and convert it to a distribution of fault time, we need the formulas, or you can do it numerically the way I did with the MATLAB. But in this case, it is possible to integrate the expression for V of t that I showed you in class to get H of t. So you get the expression in the formula here. And then, given the height, you can solve for the time using, for example, F0 in MATLAB or any other root finding routine that you want to. And then you can generate the distribution of fault time from the distribution of CD. That would be the analytical distribution. And then you can compare it to the measured distribution. So this is the comparison of the distributions, and you can see the area metric difference. It's smaller for helicopter 1, and this is because the mean of helicopter 1, 0.896, is closest to the mean of the prior, which is 1. 0.842 and 0.783 are further away. Also, the standard deviation of helicopter 1 is closer to the standard deviation of the uniform distribution, which is 0.28. And so that's why we get a small area metric, which basically says that if you want to get a good area metric when you have a wide prior for the analytical, do a lousy job testing so that you'll get a large standard deviation and you'll get a better area metric. So this is not that meaningful. Any questions on 2? Okay, so 3 was calibration, and basically, if we assume that CD is normally distributed, it's not consistent with the assumption that H is normally distributed, but the difference is rather small. We can generate a CD for each fault time and use it to update the CD distribution. And this is an example of what happens to the joint distribution of the CD, the mean of the CD, and the standard deviation of the CD. You know, you have learned about doing updating a normal distribution from samples. The main difference here is there is a prior, but that prior, I selected it to be very wide, and therefore it has very little influence. So by the time you get to 10 drops, the distribution is rather narrow. The only thing which is bad about this figure is that it was done for a different helicopter, and so it converges to a CD of 0.7, while this helicopter had a CD, the one that I showed you just in the previous slide, had a CD of 0.8 or 7.8. So if you compare what you measured with the calibrated distribution, so that the top two lines in the table are what you measure, the sample mean and sample standard deviation, and the next two lines are the peak of that distribution, updated distribution, that is the maximum likelihood point or the mode of that distribution. And you can see that you can hardly tell them apart, and this is because of the fact that the prior was so wide that it had very little influence. So had you completely disregarded the prior, you would have gotten essentially the same results. So this is, gives us the mean and standard deviation. And now if we want to go to predictive distribution, we have to do Markov chain Monte Carlo sampling. And this was done using the Metropolis Hastings algorithm, and the proposal distribution that was used is independent bivariate normal distribution, that is the distribution of the mean and the standard deviation are independent. So here is what was obtained. Oop, went too fast. Now I'm going to present the, yes.
You go to slide 6. You have the assumptions that the CD is normally distributed. I think that was the most confusing part of the whole homework, because it doesn't make much sense to me to assume that.
Yeah.
The first assumption. Well, the assumption that you can say fold time is normally distributed, and then you say assume CD is normally distributed, and it's unnecessary because we could just do it with fold time instead of CD. We calibrate as we were taught in the class, right?
Well, I give you a prior for CD, and so that implies that you will be doing the updating on CD, and so you don't need to use this assumption that the CD is normally distributed, but it provides a bit of a shortcut if you want to use it. So this is, and it turns out to be a reasonably good assumption, that is, when you have large standard deviation, then the two assumptions would clash with each other, especially if you want to go to the tails of the distribution. But near where we are looking, I think that the contradiction between the two is very small. So, but if you did it without using it, that would be also.
I did, but it was just confusing. On what the sigma test, are you taking the standard deviation from the test and using it directly as if it's the true standard deviation, or is there epistemic uncertainty on the standard deviation?
Yeah, there is epistemic uncertainty on the standard deviation because you estimate the true, that is, you have sigma test, which is what you measure from the test, and then you have sigma true, which is what you would have measured from the test had you done 1 million drops instead of. So this is where you start from, and this is where you end up, and the two are actually, in terms of the value at this reddest point, as I showed in the next slide, are practically the same, but what you get from here is the uncertainty, which is slightly different from what you would have got without the prior. Without the prior, you would have just had normal distribution that go from -infinity to +infinity. With the prior, it limits you to be between 0.5 and 1.5. So if you look at the so let's take, for example, helicopter 1 that had a mean of 0.896 and a standard deviation of 0.19. That basically tells you that because of the prior, the normal distribution would be truncated at about 3 standard deviation to the left. It cannot go, you know, if you take 0.19 times 3, and well, actually 2.5, and subtract from 0.96, you reach the lower bound of 0.5. And so that's the main effect of the prior. It kills the tail. Other questions on this problem? So the prior is not meaningless if you consider the tail. So the 5th percentile of the 5th percentile, that it can have an effect on that. Okay, so now we come to the fact that after we calibrate, we want to compare the analytical prediction to the measurements. And this is almost meaningless because the analytical prediction essentially was generated from the measurement because of the fact that the prior had such limited effect. But the experiment has less uncertainty than the analytical, because in the analytical, when we do the Markov chain Monte Carlo, we include the uncertainty in the mean and the standard deviation. So if we, in order to look at it in two ways, we have used the p-box. So if you just compare the posterior predictive distribution to the tests, you see that the red curve is sort of wider than the blue one of the experiments, and that simply reflects the remaining epistemic uncertainty due to the fact that you had only 10 measurements. If you then say, let's use a p-box. Now, a p-box requires you to have the bounds of the epistemic uncertainty, and since those are quite wide, we use the 95th percentiles, and then it looks like this. That is, the blue and red curves are the 5th percentiles, the 95th confidence bounds on the analytical or posterior distribution of CD. And now when you put in the experimentally measured one, it fits snugly in between. Not completely. If you think about 95th confidence limit, you expect 1 in 20 experiments to fall outside. And we have here 10, 10, and 10, you know, for 3 helicopters. So indeed, it appears that 2 measurements out of the 30 fell outside the box, which is very reasonable for the fact that we are using 95th percent confidence limit to describe the epistemic uncertainty. So now the area metric looks almost perfect, and it should look perfect because there is really no difference between the experiment and the theory. That is, we had a single parameter to calibrate, and we calibrated it. So why should there be any difference? Yes?
Can you explain again what standard deviation you use to make that P box for CD?
The P box for the proceeding wasn't made with a standard deviation. For when you generate, was it 100,000 or 10,000? I don't remember. Distribution of the mean of CD and the standard deviation of CD, each one of them gives you a CDF. So for each value here, let's say you take 0.2. For a CDF of 0.2, you have 10,000 values. And you take, you know, the 250 and the 9750, and you get what you see on the next slide. So this is this is the way it should be. That is, when you calibrate a single parameter and you measure a single quantity, you know, in some of the examples that Professor Choi did, you calibrate a single parameter, but you need to match a curve. Here, I calibrate a single parameter, and I need to match that parameter. So why should I have any difference? Any, yes?
So the graphs that you put up is a CDF of fall time. So is that actually the CDF of the drag coefficient calculated using the fall time data?
No, I'm so we have the posterior, we have the distribution of CD, and for each one of them, we can calculate fall time, and that's what I'm showing here. The reason that we are going back and forth between CD and fall time is the thing that we are trying to verify is the dependence on the drag on CD. And so one of the questions was, is CD constant? And so, yeah. Other questions on 3? Okay, so now let's go to the predictive validation. And again, we will have these two flavors. One flavor is to, we change from 2 paper clips to 1 paper clip, and we ask, can we predict what will happen? We calibrated with 2 paper clips. How good is our calibration with 1 paper clip? And you can see that when we look at the predictive distribution of CD for 1 paper clip, we have moderate area metric for 0.19 for helicopter 1 and a substantial one of 0.38 for helicopter 3. We look at the CD that is supposedly the same, and for helicopter 1 that we measure 0.896. Now with 1 paper clip, the mean is 0.916, not too bad, but for helicopter 3, the difference is huge, 0.783 and 0.968. And so it doesn't look too good, but this is including the sampling uncertainty. So if we go instead to a P-box, we see that helicopter 1 fits nicely in the P-box. It looks just a tiny bit less good than it was originally, but helicopter 2 and helicopter 3 look substantially different. Now you can ask yourself, how bad is 0.11 and 0.22? And my answer to that is that it's rather bad if you think about it, that we are predicting reasonably close to where we started from. That is, the mass, the change in the mass is of the order of 20% or so. And so it's disturbing that we change the mass so little and we get already substantial difference. And it basically points out to the fact that with one paperclip, the helicopter is often behaving quite differently with two. Actually, when I first used this helicopter, the dimensions were different and we got very well with one paperclip. And then in a subsequent year where we moved to the dimensions used for this helicopter, the student reported that with one paperclip it was sometimes misbehaving. And I think that that's basically what happened here. That is, the way it rotates is somewhat different, and therefore you see the substantial difference in CD. Let's see. Any questions on 4? Yes.
Did you say earlier that for helicopter 1, the mean was closer to the mean of the
Two clips, yeah.
Yeah, because we're 2 clips. Could that affect why even when you take away 1 clip, it matches up better than the other 2 since those are already further off?
Yeah, so that's what you see. 916 and 896 are close, and so it fits reasonably well in the P-box. 783 and 968 are quite far, and that is reflected in the fact that it says, no, you cannot calibrate CD based on 2 paperclips and make a good prediction for 1 paperclip. Other question on 4? I'm skipping 5 for a moment because 5 is the linear model and 6 is the quadratic model for different height. So we couldn't make a good prediction when we changed the number of paper clips, but the question is, can we make good prediction when we change the height? So instead of a height of 148 inches, we have a height of 181 inches, and we look at the results of the prediction, and without the P-box, there are now substantial differences for helicopter 1 and small for helicopter 3, but this includes also the sampling uncertainty. And so when we add the P-box, we get results that are quite good. So compared to what we had for predicting the effect of removing a paper clip, we get good prediction for the height. Unfortunately, this can be a bit misleading, and the reason is that most of the time this helicopter is falling at a steady state speed, and so changing the height has only a small effect on what happens. So if we were able to do this when the transient part was a big part of the total, that would have been more meaningful, and such an area metric would have been more meaningful. And the only reason that I didn't suggest that you drop the helicopter from about this height to begin with is because there is this initial part that we don't even model when it drops like a stone before it starts rotating. So this is a place where you can say you are making a prediction so close to the initial condition that the area metric is good, partly because of that, not only because the model is good. Any question on 6? So problem 5 was to see if you can get good results with the linear model. And when you start, you don't get very different results. The CD is somewhat different, and this is because instead of having a v-square dependence, I fixed one of the v to v0. And so I didn't fix it specifically for this helicopter. And so you got some small differences. And you look at the area metric, they look bad, but this is, as I said, because of the fact that we have small standard deviation of 0.1 and 0.05 compared to the 0.28 that we start with the prior. Yes?
One of the things that also confused me, since the prior specified to be 0.5 to 1.5, and we can change the VO to something representative of whatever we want to use, we get different values for this if we use the same prior, because we're changing the equation for CD.
Yeah. The point is that, again, I wanted to have a prior that would be likely to survive anything that you would measure. And so for the linear model, I picked up a velocity that I consider to be typical. Of course, had I chosen an unreasonable velocity, would have gotten a substantially different CD, and it would have been outside my prior. There is something here for me that I have to confess. I've been doing this helicopter project in an optimization course for the last decade, and I never bothered to see how uncertain is the CD. So this was sort of gratifying that it fell more or less where I expected it to be. So this is a summary of the results for the linear model. First of all, in terms of predictive validation, and then in terms of P-box. So when you go from 2 paper clips to 1 paper clip, you get, so first of all, for 2 paper clips, when you do the predicting validation, you get small values, and like the quadratic model, when you include the P-box, you get 0. And if you think about it, as I say, you are calibrating it for a single value, and so even if the model is lousy, for that single value, you should get good area metric. However, what is not expected is that when you go from 2 paperclip to 1 paperclip, you get good area metrics, and this time things are reversed. Helicopter 1 is not so good, and helicopter 3 is perfect. So it looks as if helicopter 3 behaves linearly with the number of clips, while helicopter 1 behaves quadratically. Now, I'm going to just flash the figures that go with it and jump to the table comparing the results of the linear and quadratic. And essentially what you see is what we just said. If you take the P box for the linear one, helicopter 1 has 0.13, helicopter, the quadratic has 0.01, while for helicopter 3 it's reversed. The linear model has an area of 0.02, and the quadratic has a value of 0.22. So the bottom line is that this set of experiments leaves us with ambiguous result as to whether linear is better than quadratic. So these are the concluding remarks, that for both quadratic and linear model, predicting for different mass was only a partial success. One helicopter did very well, one helicopter was lousy, and one was in between. The predictive validation for different height is a success, but the assumption of constant CD is not clearly proven, and this is because of the fact that it's not very sensitive. That is, the non-constant CD would have shown itself in the transient part, not in the steady state, and we have cases where most of the time it's in steady state. So for the comparison between the models, we cannot conclude. And so the reason for the difference in the area metric for the different helicopters is not clear, but it's pretty sure that we can blame the manufacturing uncertainty. Could be even where the paperclip is positioned in on the helicopter. So this is where, of course, what you get from one set of experiments, and you can possibly reach much firmer conclusion if you take several sets of experiments. There was the one set of experiments where with one paperclip, it fell faster than with two. So essentially, with one paperclip, it took it forever to reach the rotation, so that it fell a big part of the way like a stone. So that just shows you that experiments are not so easy in terms of comparing them to theory. Any questions on that? Yes?
When I did this, I took all the helicopters and put them in one data set and used it as a model for a helicopter, a generic helicopter. So what is the rationale between for splitting it into 3 different data sets.
Okay, so the reason that I did it for each helicopter separately is because the manufacturing uncertainty is larger than the testing uncertainty, substantially larger than the testing uncertainty. And partly that has to do with the fact that we can easily do 10 drops, but building 10 paper helicopters is quite a challenge. And so if you get ambiguous results for the same helicopter, if you have, if you put all 3 together, then things become even more ambiguous. So this was my rationale for doing it 1 helicopter at a time. Other questions? Okay, let me just show you the 3 slides that we selected as most as the best slides. Caitlin Harris used a different set of results, and she summarized it in a table and thought that, you know, if you have to shrink everything to a single slide, that was a good way of going about it. Let me first jump to the last one, which is Yongmin. What is this? Yongmin Zhang. He chose a different way, which I also liked, of squeezing a lot of small figures into that. And I figured out if my eyes can still make sense of them, then yours should do that without any problems. And then this one by Nikki Lond is a minimum of figures and maybe the simplest. So if you want something reasonably simple, that would be a model to shoot for. These 3 different models of generating slides have to fit your style of presenting and the needs of the people who are looking at it. That is, a lot of time, program monitors at funding agencies would ask you to squeeze everything that you have done during the last year into a single slide. And then you have one challenge. And at other times, you squeeze things into a single slide for a single lecture, which is a different thing. And it's a third time, you use the slide as a way to remind yourself what you are talking about, which is a third usage. So no one model fits all, and these 3 are not bad examples of reaching for a compromise in a different way. Any questions? Okay, well, good luck on the exam and hope that you don't need to take the optional final.